Hello everyone, I'm John Park, a PhD student at Korean University. Today I will give a presentation of our work, Transferable Model-agnostic Vision Language Model Adaptation for Efficient Weak-to-Strong Generalization. Vision language models, such as CLIP, are trained on large-scale image text data, which endows them with strong zero-shot capabilities. With only a few labeled data, they can be further adapted to become domain experts. And nowadays, vision language models are rapidly evolving in terms of architecture, pre-training data, and learning objectives. However, repeatedly adapting each new model remains computationally and memory intensive. This leads to a natural question: can adaptation knowledge learned from weaker earlier models be reused to improve stronger newer ones? This idea forms the basis of weak-to-strong generalization. In this work, we tackle three fundamental limitations that existing adaptation methods face in weak-to-strong generalization. First, many adaptation methods are model-specific, which makes cross-architecture adaptation transfer fundamentally infeasible. For example, prompt-based adaptation introduces learnable tokens for vision transformers, but this mechanism cannot be applied in convolution-based models such as ResNet. Secondly, even when transfer is partially possible, additional costly training is required to align the adaptation model with the target model. For example, to match the feature dimensionality and representation spaces. Finally, reliance on multiple models, such as ensemble-based approaches, introduces substantial inference time overhead. To address those limitations, we introduced TransMiter, a lightweight adapter that improves any vision language model without backpropagation. Overall, TransMiter works in two steps. We first extract adaptation knowledge once, as the gap between pre-trained and fine-tuned weak models. This knowledge is then transferred to any pre-trained strong model, enhancing it into domain experts. In perspective of the performance, our goal is to preserve the strong model's pre-trained knowledge while clearly outperforming the fine-tuned weak model, and to further approach the performance of a fine-tuned strong model. During adaptation knowledge extraction in TransMiter, it is trained in an unsupervised manner using a KL divergence loss, increasing its output losses to mimic those of the fine-tuned weak model. For transferability, TransMiter operates on logits rather than intermediate representations, allowing the adapter to be attached to any model. We further introduce auxiliary classes to increase logit dimensionality, which maximizes transferability. For efficiency, the model is composed of only simple projection matrices and a single MMP layer, which minimizes additional inference cost. Finally, to preserve pre-trained knowledge, the inner and outer projection matrices are shared and orthogonal, which ensures they are immutable and retain the original model behavior. After adaptation knowledge extraction, we transfer the learned adapter to the strong model. A key challenge in this process is the logit distribution mismatch between weak and strong models, since TransMiter is trained on the input distribution of the weak model. We address this issue by performing linear alignment between the input feature distributions of the weak and strong models using a closed form solution known as orthogonal progress test. This alignment is performed without backpropagation, enabling efficient transfer of adaptation knowledge. After the alignment, we transfer the adapter by updating the projection matrices. Specifically, the projection matrices of the target model are updated by multiplying the learned mapping matrix with the weak model's projection matrices. The resulting projection matrices still remain immutable, which allows us to preserve the pre-trained knowledge of the strong model while injecting domain-specific adaptation knowledge. With this strong initialization, additional performance gains can be achieved through supervised fine-tuning, fully exploiting the capacity of TransMiter at minimal additional training cost. To validate the effectiveness of TransMiter, we conduct experiments under two settings. First, we consider base-to-base adaptation transfer, where the weak model is fine-tuned using all test classes. We evaluate multiple models with diverse architectures and scales, and observe that the performance gains of transmitter increase consistently with the strength of the strong model, the strength of the weak model, and the quality of the weak model's fine-tuning strategy. We also evaluate transmitter under a base-to-novel adaptation transfer setting, where the weak model is trained on a subset of task classes, referred to as base classes, and evaluated on novel classes that are unseen during training. Compared to existing baselines, transmitter is the only method that preserves pre-trained knowledge while achieving strong enhancement. In addition, we show that transmitter is agnostic to the adaptation strategy used for the weak model and can even outperform a strong model adapted with the same strategy when only a small amount of label data is available. Next, we present a series of analyses to better understand why transmitter works and where its gains come from. For the adaptation knowledge extraction, introducing auxiliary classes significantly improves the quality of extracting knowledge. For transfer, we observe that auxiliary class expansion and basis change alignment are highly complementary, leading to effective transfer. For a more in-depth analysis of auxiliary classes, we observe that higher dimensional lodges improve adaptation knowledge extraction, while transferability benefits even more, highlighting the importance of sufficient logic expansion for cross-model transfer. In terms of efficiency, transmitter is highly efficient in both adaptation transfer and inference, introducing minimal overhead compared to baselines. Moreover, when combined with a small amount of label data, additional fine-tuning remains training efficient and yields substantial performance gains, effectively maximizing the capacity of strong models. In conclusion, we propose transmitter, which enables seamless weak-to-strong transfer across diverse architectures and model scales. Our methodology, including auxiliary class expansion and basis change alignment, maximizes the transferability of the adapter, and transmitter's lightweight design ensures high computational efficiency in practice. Thank you for listening to my presentation.